case 1. So when I look at case 1, what I'm going to do here is I'm going to look at equal masses. And this should be M1 is equal to M2. And I'll probably just abbreviate that as M. So if I have this situation, I'm thinking about balls here. So I'm going to be thinking about, so what I'm really thinking in my mind here is that I'm thinking about billiard balls. Colliding. So let's look at this thing. So what am I seeing here? So you could imagine a pool table, and these balls don't rotate. So they're sliding. Rotation changes things. So what we have here is that we have sliding billiard balls on a frictionless table. So of course, the view that we're looking at is we're looking at the top view. Okay, top view. So if I look at this thing, here I come in. I have my ball, right? There's my ball, and this is 1. And that ball is coming in with what? Some initial momentum. And what I know here is that my target is stationary. So when I look at its momentum here tells me that it's 0. So what I said here is that this is my system. So a collision within this system must do what? The collision within this system is all internal. If it's all internal, the total momentum of the system cannot change. So if I look at this here, what does my bar diagrams look like? Well, if I look at my bar diagram, I'm seeing that I have, let's say, this amount of momentum coming in. And I know that that momentum is going to the right. And so what I'm going to do here is that I might as well say to the right is positive, going to the left. And then beforehand, we already know that the momentum of P2 is 0. Right? That's what my system is telling me. So the question is, what happens afterwards? Right?
All energy transfers.
All energy transfers. But the question that I'm asking, which ball has more momentum after the collision? Is it the projectile or the target?
All energy transfers to the target.
And I would agree with you. Because when I go and I look at this thing here, the only way, I mean, is that billiard ball 1, is it going to go into, is it going to go through, is it going to burrow through particle 2? The answer is no. But all I know is that this is my total momentum. And according to my elastic equations, so let's look at my elastic equations. We're seeing here is that V1 final should be M1, M2, M1 minus M2, V initial. But wait a minute, M1 and M2 are exactly the same. So we're seeing that this numerator is 0. So that means that the speed and momentum of the target, of the projectile is 0. that means that when I look at the momentum of this guy, afterward, it's zero. The only way that could be true here is if what happens, looking at my elastic equations again, look that the masses M1 and M2 are exactly the same. So that means that this must be the same, oops, that's initial, that this momentum of the incoming red billiard ball gives all of its momentum to the second billiard ball.
Would you draw that in the negative direction? Or
No, it would go to the right.
oh yeah, it's the right. Yeah.
Because remember, it not only does it have to conserve magnitude, it has to conserve direction too. Now, look at that statement that I was making. Where did I write that at? I said it up here. The momentum of individual particles must redistribute their momentums in order to conserve it. And in two particle collisions, guess what there is? There's an exchange of momentums. Look at this. These guys exchanged momentums. So you could see that these two guys exchanged, and then these two guys exchanged. There's literally an exchange of momentums.
And is it because momentum's mass times velocity that you're in a sense, like the velocity is the vector component. So in a sense, that's where the exchange of, is there like an exchange of direction in a sense, or like
I think that
the
it's
direction part's a
not,
little tricky?
it's not an exchange of direction. It's of exchange of mass times velocity. Momentum is not just velocity. Velocity is not fundamental. Mass times velocity is fundamental. That's a constant of nature, which I think is really surprising. Mass is not a constant of nature. Velocity is not a constant of nature, but mass times velocity in this context is a fundamental constant of nature. And so what I want to do here is that I want to go in and show you this. And so what I'll do here is that I want to come in and show you exactly what it looks like. So when I look at this thing, here's what I have. So the masses are not the same. So let's make them the same. So this guy should be 0.5. So now they're the same. Now I'm going to give them the same velocities. So this guy, how about if I make it 0.25? And the other one, I'm going to make it negative 0.25, so that they have the same velocities and masses. But wait a minute, once at rest, I almost made a mistake here. I want one to be at rest. And what I'm going to do here is that I'm going to, that's not what I wanted to do. I got to put this guy at the origin. So let me enter that again. And this guy I'm going to put at the origin. So here I go. Check out the velocity of center of mass and look what happens afterwards. And there's an exchange of momentums right there. Right? That's the exchange of the momentums. So before and afterwards, you're getting these collisions here. So that's what I mean by that. So if I was to look at this thing, I could do this. So if I look at this system here, right? If I look at this system, I'm going to bring this into my OneNote. And then what I'm going to do here is that I'm going to play this again. And what you're seeing here is that you're seeing the following thing. So if I bring this into my OneNote so that I could show you. Let me get one more image. Now let me share my screen with you. And this is what you're seeing. So what you're seeing here is that picture-wise, this is before. And the fact that this thing is moving, this guy is again our center of mass. Or I could say that's the total momentum line. And they're moving like this. And then this guy starts off at rest, right? In this case here, we know that this is initially at rest, and this guy's coming in with some velocity, V1 initial, that's not zero. And then afterwards, you're seeing that after the collision, we're seeing here is that this guy ends up at rest, right? So this guy now has at rest, and this guy's now moving with the velocity to final, which is the same velocity that was incoming. And at the same time, this guy still has V center of mass, total momentum going to the right. That's what we're seeing right there. So there's a redistribution. So now let me ask you a slightly different scenario here. We're still with the same mass. Now suppose V2 initial is not zero now, but V1 initial is faster moving than V2 initial. Okay. So in this case, what I want you to pay attention to when we look at this thing, if I look at the momentums, let's look at what happens to the momentums here. By the way, I want to set this up so that these masses are not the same. Okay. So what you're going to see here, oh, how am I going to draw this up? Oh, I know what I want to do. I want to be careful how I say this. No, I want to keep the masses the same. I don't want to exchange the masses just there. So what I want to do here is that, so my picture looks something like this here. So the first thing that I'm seeing is that I have my red ball coming in like this. And then I have my green ball coming in like this. Remember, they have what? They have the same masses here. But I do know that one is traveling faster than the other. Let's look at the picture here. So this time, if I draw my momentum bar diagram, what do I see here? Well, I know that this guy is moving with this amount of momentum. And I see that the green is now coming in the negative direction. Again, remember, we still have the same type of system. So the green is moving slower, but it's moving in the negative direction. And of course, that's got to be momentum 2 like this here. So what you're seeing here is that afterwards, what has to happen? Well, one of the things that I said up here is that what happens? There's an exchange in momentum. They exchange momentum. So what I should be seeing is this, that red particle should be doing what? It should now have a momentum that's smaller going in the opposite direction. And the green now has a higher momentum going to the right, like this. And what we'll do here is that, let's go set this up in the simulation here. So if I come up here and let me do a new share, and it's going to look like this here. So now I'm going to change, I'll keep the masses the same. And what I'm going to do here is that I'm going to go look at this velocity. So this velocity, actually, let's not do that. I'm going to move this guy over here. And you could see that the masses are the same, but this guy has a higher velocity. And I'm going to move this guy over here. And this guy has a slower velocity. So then check this out. Look at the speed of 1 coming in. Look at the speed of 2 coming in. And then look what happens to the speed of 2 and 1 afterwards. Here I go. Check it out. See how 2 is moving much faster than 1? That's because they exchanged momentums now. That's what I mean by the momentums of the individual particles must redistribute the momentum to conserve the center of mass. It gets more complicated when the masses are bigger. So now if I come in here, for example, and I make 1 like this, what you find here is that this is more difficult to actually then come in and just say, so what actually happens here? Well, look at that. They're approximately the same, but look where most of the momentum is going to be. It has a bigger mass. Excuse me. They roughly have the same mass, the same speeds, but in opposite directions. But let's put them exactly the same. So now look what happens. We looked at speed beforehand. Now we'll look at mass. So if I look at the total momentum, look at the chart. It's still going to the left. So now look what happens here. It's the ratio of masses now. And that's what the elastic collisions equations will tell you. It's the ratio of masses. And we see that by these equations here.